gravity is not about particles accelerating, as one thinks about it in ordinary physics and Newtonian physics. In fact, what gravity is about is inertia. Inertial particles, when encountering a region where there is matter, they're all still inertial. Just they experience a relative acceleration. We thought of the medium before as space, and now we understand the medium as spacetime. It has an effect on the medium, spacetime, such that although inertial particles remain inertial, they experience a relative acceleration. So now we would say, okay, we had a very beautiful model of what inertia is, right? Inertial world lines are geodesics of spacetime. Can we now use this model for a region where there's gravity? And here we have two inertial particles, parallel, straight, geodesic world lines. All right? Right? And there's relative acceleration between the particles. So now, there goes our model. Right? I mean, this is certainly not geodesic. Right? If these lines curve towards each other, away from each other, they're not geodesic. So, although we have a very nice model for real inertial particles, in other words, in the absence of gravity, where the absence of gravity really means where no measuring instrument of ours can ever detect anything that we can attribute to gravity, because really there is gravity everywhere. But so no gravity means we can't detect it. So there we're satisfied with our law of inertia. Inertial particles have geodesic world lines, geodesics of spacetime. But that only works, like I said, when you can't notice any gravitational effects, because once you are in the region where gravitational effects are experienced, namely, what does a gravitational effect means? Relative acceleration of these inertial particles, then your model fails. Of course, Einstein said, no, I'm not giving up my model. So, well, how do you, I mean, this is definitely so. And you can see that mathematically, you can see that intuitively. So what Einstein said is, I like my model, I don't care. If this happens, then that's what's going to happen. So you say, well, then they're not geodesics. He says, no. They are inertial, and they are therefore geodesics. Both of these are geodesics. And you laugh, you say, well. You say, no, space-time is warped. Your diagram is a diagram of Tx for space-time when it's not warped, when you can't feel any gravitational effects. It's simply not applicable to regions of space-time where the effect that we call gravity can be measured. How do you draw it? You can't really draw it. You can do it mathematically. And I'm going to define, you'll say, well, what do you mean it's warped? You say, well, I'm defining warped. Warped space-time is such that it has geodesics, just like unwarped space-time has. It has geodesics. The notion of geodesity, of straightness, can be defined in it. And I'm just saying that. I'm taking that as given. And it also has the property that despite the fact that these are geodesics, there will be this, and we call it deviation of the geodesics, which translates, of course, into, if this is a map of space-time, then it translates into relative acceleration of neighboring inertial particles. And you'll say, well, you're just kind of, we had an objection, and you're just saying, well, the question that we asked is really the answer. Say, yeah, that's right. We had a problem. How do we map geodesics that deviate? So I'll say, well, I'll just define a space called a warped spacetime. And what I mean by warped is exactly this, that although it has geodesics, the geodesics experience geodesic deviation, the type that we mentioned. So, well, then becomes a mathematical problem. Can you do that? Can you define such a space?